All right, welcome everybody. Sorry, we had some shuffling with the rooms at the last minute, so just getting up here. So I am Trey Grainger, and today I'm going to be talking about building AI models with OpenSearch's user behavior insights. If you don't know me, I am the author of the book AI-Powered Search, and I'm also the founder and CTO of Search Kernel, which is an AI-powered search consultancy company. I'm also, we just announced last week that I've signed on as a technical advisor for Open Source Connections, who's here at the conference. So any of their clients can also get access to me for needs with AI-powered search capabilities. I'm also a professor teaching computer science at Furman University. Previous roles I won't get into, but worked for a decentralized search engine, so CTO. Was the SVP of engineering and chief algorithms officer at LucidWorks, a search company, and just been doing search most of my career. The agenda for today, we're going to, first of all, introduce AI-powered search and the concept of reflected intelligence. I'm going to briefly introduce user behavior insights and talk about how it works. And then we're going to get quickly into building AI models for AI-powered search. I'm going to talk about 4 different kinds of models. Popularized relevance models, like signals boosting models, personalized relevance models like building user profiles and doing personalized search, and collaborative filtering, and generalized models like learning to rank, and knowledge graph learning models like domain-specific semantic knowledge graphs. So first of all, what is reflected intelligence? You're probably all familiar with feedback loops, reinforcement learning. It's a very similar concept for search. The idea is a user runs searches. They see some results. They take some action on those results. And then the system collects the queries, the actions they took, and learns from the user behavior, what users like, their taste, their preferences, what is relevant. And based upon that, builds models to reinforce relevance for future users. So it's just a giant and continuous feedback loop. In terms of building these models, they typically rely on user behaviors. In this talk, I refer to them as signals. And the idea is that when a user runs a search, for example, iPad here, their data gets collected, who the user was, their ID, the query they ran, the results that they saw, and the order they saw them in. The users then take some action based upon the results they saw. Those actions are also recorded. Signal processing and machine learning can then take place to build all kinds of machine learning models, and then those learned relevance models get pumped back into the system to influence the relevance of future searches. There's many different types of these reflected intelligence models. I've got just a few here. We talk about all of them in the book and have code and examples of how to build these. But everything from signals boosting feedback loops to collaborative filtering and personalization feedback loops, automated learning to rank, by learning implicit judgments from click models from user behavior, and then all sorts of other ones over here about building personalization profiles, et cetera. So those are the types of things that we can build if we have user behavior data. So the question is, how do we get the user behavior data? So thankfully, Stavros is sitting right here. The user behavior insights capabilities that are now in OpenSearch, or available as a plugin being in OpenSearch, or how we can make that happen for OpenSearch. So if you didn't see the talk earlier with Eric and Stavros and Aruna, definitely check that out when the video comes out. They talked about collecting data in user behavior insights. They showed some dashboards about different amazing things you can do with the data. In this talk, I'm going to be focused on the machine learning model side of what you can do with the data. And so this is if I'm running a search in OpenSearch with UBI, I can basically configure it so that I can either have it generate some of this data for me automatically, or when I run searches, I can pass in a query ID, the user ID, and sort of the field in which, for example, all my examples in this talk are product search, the field in which the items are that the users are going to interact with, in this case, click, add to cart, purchase, et cetera. And then UBI stores all of that data. So there's a queries collection, and there's also an events collection. I don't have an example of the events API in this talk, but refer back to Stavros' talk from earlier. The queries get logged, the results the user saw get logged, and then all of the follow-on events, clicks, add to carts, purchases, et cetera, get added through the API. And once that's done, the data is in OpenSearch. Now, for purposes of the book, we have a slightly different signals format. It's very comparable and compatible. So what we've done for the book is we've generated a Jupyter notebook that can take the UBI format and convert it directly into the format that's used to build all the machine learning models in the book. So if you get a copy of the book and you're using user behavior insights, you can immediately run all the Jupyter notebooks and see what kinds of relevance models are built for you. So pick this up and run it. In this talk, I'm going to talk about 4 different categories of reflected intelligence models or machine learning models based upon these user signals. One is signals boosting. I refer to this as popularized relevancy. So this is the idea of learning exactly what items, what documents users want to see based upon their queries and making sure those are boosted to the top. The second category is LTR, learning to rank. I refer to this as generalized relevance. This is the idea of using user behavior to learn a general ranking algorithm that doesn't matter what the query that comes in is, you can use that model to boost results up and down. And then the third is collaborative filtering. This is used for personalization. I'll show both collaborative filtering examples and other personalized search examples based upon the underlying concepts behind collaborative filtering, i.e. matrix factorization. And then the last, and that's a personalized relevance category. So in this category, users get customized results to them, either recommendations or results nudged up and down based upon their likes and their interests. And then the last category is knowledge graph learning. And so we typically think of knowledge graphs or semantic search as something that's derived mostly from documents. We either have a large language model that was trained from text, maybe we fine-tuned it from our own text, or maybe we've got some other data, but usually we think of it, semantic search is related to the text and the content. But the user behavior signals, the queries users run, the documents they click on, those can also be used to learn domain-specific language, things like misspellings, things like related terms. And so I'll show an example of that as well. OK, so for the first category, popularized relevance models, we're going to talk about signals boosting. And so this is your typical search. I've got a product catalog here that's loaded up. And with BM25, the default lexical ranking algorithm, what you get when you run your search is results that look like this. The reason you get these results is because, well, the name is iPad. That makes sense. iPad is in the name, so it's matching on the title, so it's getting a high boost. But also, this particular product happens to be mislabeled. The company, the manufacturer, is labeled as iPad, which isn't correct. So these actual third-party kind of bad results end up going to the top just because there's a text match on fields where the data is not even correct. So this is obviously not the kind of result you want to get for a query for iPad. So we'll put on our AI, machine learning, relevance engineering hats, and our we'll be relevance engineering ninjas for a second. So if I look at the problem and I look at the data I have, I realize I've got people shopping, purchasing. People who are running the search for iPad are usually purchasing these things. So I'm going to use that information to build a signals boosting model. So this is the same general diagram you saw earlier for reflected intelligence. This is just a very specific application of it. What we're doing here, same query for iPad comes in. We log all the UBI information, the query signals, the behavior, the event signals over here for clicks, purchases, et cetera. And then we take that data and we apply an aggregation on top of it. And we aggregate all the signals to figure out what, for the query iPad, what are the top products that people actually purchase. And what we find is that this document and this document get by far the most results for this particular query. The most purchases, let's say, or the most clicks. This one right here by a wide margin. So we literally take those aggregated values and we boost relevance based upon them. This is the format that the book uses. It's very complementary with the UBI format. We've translated from UBI into this, but we basically have query ID, a signal time, a user, a type, and the target. In this case, it's the product. And then from that, we run this code to do our signals aggregation. we end up with these aggregated signals over here. And from that, we now have this list of boosts. So these particular products are going to be boosted by this amount based upon the number of clicks, the number of purchases, et cetera, that happened on those products based upon the search for iPad. We then convert that into a query to do boosts at query time. And then the next time somebody runs a search for iPad, then this is what the results look like. Very clear and marked difference from what we had before. And this is all based literally on looking at what users do and boosting the results accordingly. Comparably, you can imagine if you worked at Home Depot and somebody came in and said, hey, can you find me a hammer? And you don't actually know what aisle the hammer's on, but you tell them aisle 12. And then you see them walk out of aisle 12 5 minutes later really confused, walk down to aisle 17, and then walk out with a hammer. And then another person comes in the door. They ask you where a hammer is. Aisle 12. You see the same behavior. Another person comes in the door. Aisle 12. And you do this for days, for months, and for years. That's what we often do with our search engines. We plug them in. We use BM25, basic ranking. We never learn from users and adjust the behavior. And so signals boosting is literally watching the aisles people go down, figuring out where they're finding what they're looking for, and then making sure that's where you tell people to go next time. Those are the products. Those are the documents that you show them. So before and after. Very clear that's how signals boosting works. That was a very naive model for signals boosting, though. So there's a lot of things we can do to improve it. I'm going to go very quickly through these just to give you a taste. All these techniques are in the book. All the code for doing this is in the book. But one of the things you want to do is normalize the queries. So we know that queries and just text in general is messy. So this is an example of the top queries that are basically leading to actual iPad products. You see multiple variations, uppercase, lowercase, spaces, numbers. It's kind of all over the place. These are case differences, for example. These are case differences and white space differences. Case differences, white space difference, and stemming differences. So if we do some basic case normalization, we just lowercase everything, all of a sudden we go from this list to this slightly more clean list, and you notice that the signal boosts are actually much more focused. What we've done is we've eliminated a lot of noise from the signals and aggregated them to make them more powerful. Similarly, there's other, obviously, ways you can improve these, but these are just some of the techniques you will want to apply in a real production scenario. Also, signal spam can be an issue. So if people learn that your search engine is using signal boosting, and they want to mess with your search engine, they can do that very easily. So for example, if this individual is going to search for iPad, they might determine that the iPad they want looks like this last document in the results. So they might click it a whole bunch of times. I don't know, maybe they click it 5,000, 10,000 times. And all of a sudden, the next person that comes to your search engine, this is the top result for iPad. That is not what you want, and you don't want people to know that they can do this to your system. So you implement some spam filtering in your capabilities. So this is an example I use in the book. I just imagine a user who is really frustrated with Star Wars. They think all the recent Star Wars movies are garbage, Disney's ruining Star Wars, and they want to make sure that everybody knows this. So they come to your search engine, they find a garbage can that is a Star Wars garbage can. So they make sure that every time someone searches for Star Wars, they see a garbage can at the top of the results. Very doable if they just, if they influence your signals boosting model. So all you need to do here is just make sure that every user, assuming you can track your users, every user can only count once towards each signal. And so this is very basic modification to the signals boosting algorithm. Once you've done that, then your original signals where the user wasn't doing anything, there's no boost for this trash can. After he did the signal spam, he had this massive boost because he clicked on it 5,000 times or added it to his cart 5,000 times, et cetera. And then after the signal spam, now he's only got a weight of 1. So there's still some influence, but it's not enough to be material. So now you get back to the results you're expecting for the query Star Wars. There's also things you're going to want to do to combine multiple signal types. Obviously, you've got clicks, add to carts, and purchases, and an add to cart is probably a higher signal, more valuable signal than a click. A purchase is a really valuable signal, so you can weight these relative to how much they should contribute. You can also use negative signals boosts. So for example, if you're able to track things like, did they skip over the document? Did they remove the document the product from their cart after they added it? Did they return it, if you can somehow track that in their account? Did they post a negative review on it on your website? Those can also count as negative signals boosts that can counteract the positive signals boosts. There's also time decays. If it's job search or a news website, you're going to want to penalize signals boosts based upon how, if they're older, and promote ones that are newer. All those techniques are in the book. Here's some code for it. Play with it. Get the Jupyter notebook. All fun to play with. And then also there's some benefits to doing index time signals boosting versus query time, but that's for another talk. Personalized relevance. So that was category 1, which was the popularized relevance signals boosting. Personalized relevance includes things like collaborative filtering and personalized search. So I tend to think of personalization as a spectrum. A lot of people think of search engines as one category of thing and recommendations as a different category. I don't see it that way. For me, it's all just matching. You've got a matching and ranking engine, and they're both doing the same thing. So on one end of the spectrum, you've got context that you pass for matching. In traditional keyword search, lexical search, the context is queries, and that's all the context you have. In traditional recommendations, the context is user behavior, and that's all that you have. And so you use that behavior to suggest results, or you use the queries to suggest results. But there's this whole spectrum in the middle, this area in the middle that is personalized search, where you can actually use what you know about the user to influence the results they see for a keyword search or a semantic search. And likewise, if it's recommendations, you can use their past queries or allow them to take current queries or filters and modify their recommendations. So collaborative filtering, again, the same general feedback loop. Run a search, collect the queries, collect the activities, but now the model that you're going to build is a matrix factorization model that ultimately, when you multiply the matrices together, it generates you weights associated with the particular users and items, and then with those you can make recommendations back to the user. This is your typical users who bought this also bought this, users who like this also like this. Kind of model where, based upon what the user sees, they're going to get more recommendations based on what other similar users who've interacted with those items have seen. Here's the code. Play with it on your own. But for this user whose previous searches include Apple and MacBook, and these are the previous clicks and add to carts and purchases that they have, these are the recommendations that will get generated in the future based upon collaborative filtering, which look pretty good and relevant to what they've done when you run the code. When you try to take that concept and apply it to their searches, however, not just recommendations, but also influencing the results that are coming back, now you've got, for a non-personalized query, this list of results. So if someone searches for tablet, in my search engine, this is just a lexical matching BM25-based OpenSearch out-of-the-box implementation. I get this, which is a list of tablet sleeves, a CD from Memorial tablet, Stone tablet like these, and some chargers for tablets. Obviously not what I'm looking for. They do match the text, but these are bad results. So what I'm going to do instead is implement personalized search. And so I'm going to take their search for tablet and still run it. But among the results that are coming back, I'm going to boost results higher if they also match the collaborative filtering aspect. So this is sort of marrying recommendations with search results, or you can think of it as taking your search results, taking your recommendations that also match those search results, boosting based upon the recommendations, and then including the rest of the results. So you'll see at the bottom, I still have the lexical matches that were there before. They haven't gone anywhere. But what I've done is all the results that were further down in the list, they've now been boosted up. Just like we did signals boosting, we can do boosting on the items that have been identified as recommendations using the same techniques. In addition to the sort of raw generate me some recommendations for our user concept that we just looked at, we also can use the intermediate matrix factorization to learn latent features. So if you think of embeddings, when you talk to an LLM and you get embeddings back when you're encoding your text, what you're getting back is this long vector of numbers that each of which represents a latent feature in the embedding space, in the vector space for whatever the text was that was encoded. When you do matrix factorization on user behaviors, you generate similar types of embeddings, but you do it based upon behavior. So in this context, when I do matrix factorization, I'll show you in the next slide what this looks like practically, but I might generate embeddings that look kind of like this over here, where, and this could even just be coming from my LLM, where I've got 768 dimensions. This item has these feature values. This item has these feature values, etc. But if you sort of look at these in aggregate, what you'll notice is that this particular feature roughly corresponds with size of the item. It influences lots of other things, but size is definitely included in this particular feature. This one very much influences color. This one very much influences, is this thing kind of like a computer? I've got sort of my tablets over here, and they're very much like a computer, and my screen cover is very much not like a computer. And then this one seems to correspond with price, et cetera. So we may not know we can't apply specific labels to these, but we can tell general influence within the embedding space. So similarly, when we do collaborative filtering, we've got a bunch of users over here. We've got the items that they've interacted with. So in this case, this is movies and television shows and games and things like that. I can say that these users interacted with these items, and these were their relative preferences. These might be something you've explicitly asked them, or this might just be based upon their behavior. What types of things are they showing the most interest in? And so notice in these squares here, I don't have any activity. I just don't know. With matrix factorization, what you do is you take that user item interaction matrix, the user rankings matrix, and you break it into two matrices. You have this user matrix, or user feature matrix, and you have this user item matrix. And these parameters here, these are individual latent features that are sort of learned or figured out when you run a matrix factorization algorithm. So the goal is that this matrix and this matrix, when you multiply them back together, roughly approximate your original matrix. And so there's algorithms like alternating least squares, which I'll breeze through here in a second. But when you apply them, then you can do personalization based upon them. I'm going to come back to, hold on one second. Yeah, we'll keep going. And so once I do that matrix factorization, now I actually have a list of latent features for each user and a list of latent features for each item. And then whenever the user runs a search in the future, I can use that list of latent features to influence or personalize the results up and down. So in this case, here's a user. They've previously run a search or clicked on Hello Kitty plush toy, GE electric razor black, GE bright white light bulbs, and Samsung stainless steel refrigerator. So these are just random items that let's just say these are searches and they've interacted with. So in the future, they search for microwave. What do you want to do? Well, you could just run your basic microwave search that everybody sees, or if you know that, hey, amongst all these things, when they've looked at appliances, they've been looking at stainless steel appliances, you can try to influence. And so over here on the left is blind personalization. This is what a software engineer on your team would do if you said, hey, can you go implement personalization based upon someone's previous behaviors? You'd probably get something like this, where it would take all of the features over here, well, Hello Kitty, white, black, stainless steel, all of these things, and when they search for microwave, you're going to get this list over here. Well, here's a black microwave, here's a Hello Kitty microwave, here's a white microwave, and there might be some other things from here influencing it. But even though this does match all of their past behavior, these aren't very good results. Can someone tell me why these aren't good results? Anyone in the audience? Do you think a Hello Kitty microwave is a good result if someone previously searched for a stainless steel refrigerator and a Hello Kitty plush toy?
I want it.
You want it?
That microwave, yeah. Relevant for me, I guess.
Would anybody else think these are good results? Maybe?
They're all GE also.
Oh, they're all GE? Oh yeah, because they search for a GE razor. So of course they want a GE appliances because search for a razor, right? So the problem here is that there's no guardrails applied. And so just because, if I like the movie The Terminator, and I go to the store, and they start recommending guns to me because I like the movie The Terminator, that's not what I'm looking for, right? Just because there's some correlation, in different categories, there's different things that you're looking for. So over here on the right is an example with personalization with categorical guardrails applied. So what happens here is we identify that microwave is from the category of appliances, and then within that category, we look at what types of things have people shown an interest in. And so I'll show you an example of how to do that. But basically boils down to clustering. So if you take all your products, and you cluster them into different categories, and then you look at so there's some code to do that. I would end up with something like this. This is my giant, n-dimensional matrix, squished down to 2 dimensions for viewing. But what you see here is that, okay, well, this is all the like CD music kind of stuff here. This is the DVDs here. So this axis, is things that are like sound and things that are visual. So down here I've got TVs, for example. Up here I've got guitars. But also, over here I've got like computer memory versus, devices and things. So if you sort of think of this as a vector space where all your products have been kind of placed based upon some semantic similarity to each other, what I can do now is take a query, and when it comes in, I can figure out which of these clusters, there's like 100 clusters here, which of these clusters or which of these clusters plus the nearest 5 or 10 clusters are related to my query. And then from that, you can look at, well, what behaviors has the user had within those clusters? And then you can boost up and down based upon that. And you can ignore all the other categories that are just too different for you to be able to apply personalization signals across them.
So what happens when someone searches for notebook, which is both stationary and computer?
Yeah, so if you don't know what the word notebook is, it's like just a typical, this is my rule of thumb for semantic search. If you know that user has been looking for other computers, for example, then I would use that to choose the meaning of the vector that I'm going to use. I would use their past behavior to influence the semantic meaning of what they typed in. If you have someone who comes to your website for the first time ever, you don't know anything about them, then what I do is I pick the most popular meaning of notebook, either the like writing on a paper notebook or a tablet or what have you. What's that? I don't. I personally, I don't like to see lists of results that are just mixed. If I search for driver and it's like, here's a golf club and here's a printer and here's a Uber and here's a van and here, I'm just like, what in the world have you done? Your search engine is dumb. It has no idea what it's doing. So I would rather take an opinionated stance usually, show them something, and if it's not the meaning, it'll be very clear to them what happened, and then they can refine the query to say, no, I meant computer notebook or tablet or what have you. That's just my personal preference. I'd rather avoid confusing the user and making a mess and just be more opinionated. But yeah.
Somewhat tangentially, you can also provide a list of
absolutely. You can provide categories.
Say
Yep.
notebooks and blah, blah, blah.
Yeah, absolutely. From a UI standpoint, guiding the user towards a specific meaning is obviously best. So yeah. So anyway, so in this particular context, what I've done is I've mapped the user's query into clusters. And so they search for microwave. And what I've done is I've said, well, from a k-means standpoint, this is the closest. From a cosine similarity, this is the closest. But what I like to do is, for example, in this case, look at the top 5 closest and allow any signals from those categories to influence. So skipping over the code, this is how you generate a personalization vector for the user's query. This is how you generate a contextual personalization vector based upon the clusters. And I've generated a couple different variations here that I'll show on the next slide. This runs the search. And then at the end of the day, what you have is, someone searches for microwave. This is the plain BM25 results they would get. So here's a microwave, it's white. Here's a microwave, it's stainless steel. Here's some microwave popcorn popper, and here's that beloved Hello Kitty microwave down here because it's apparently very popular, as it should be. The next category is personalization without guardrails, what we showed a minute ago. You already saw this. Hello Kitty goes to the top because the user likes Hello Kitty. And then you get a stainless steel microwave, another stainless steel, and then a white one down here. And then this last category has learned that user is looking for stainless steel appliances, shows them stainless steel appliances, and I think, I don't know if they searched for Panasonic or what it was before, maybe it wasn't, but anyway, it was a Samsung earlier, so maybe maybe the vector doesn't include any concept of Samsung. But either way, they're stainless steel, which is fairly good. And then the nice thing about this is as they change their behavior, they run in searches for other things, you can use the most recent queries and those signals to determine on the fly what your personalization vectors are going to be. So this isn't an offline learning static thing that you could very well just look at their current session, you could look at their last 5, but it evolves as the user evolves so the user doesn't get stuck in some personalization profile and have to call customer service and yell at them because your engineers are not doing a good job. So one other nice thing about using these latent embeddings from behavior is that you can also you then combine them with other modalities for vector search. So in this case, I've got this user, he likes Avengers Endgame, gets a high score for that. I've got this user, she likes the movie The Notebook. This may or may not be modeled after my wife and I'm just saying. But you get these users, and they have these particular preferences, and then you can use that as an embedding, and you can combine it with other types of embeddings and sort of create a model that can sort of go across embedding spaces. So for example, we're very used to at this point taking text and creating text embeddings, taking images, doing image embeddings, and in this case I'm just saying the user behavior, the things the user has done, the items they've interacted with, those can also be added in as embeddings. You can sort of create a joint model that can sort of understand the relationships between these things, then go from there to influence your search results. If you're interested in more on personalized search models, chapter 4 and 5 of the book cover those in great detail. The last two areas I'm going to breeze through kind of quickly. One is generalized relevance or learning to rank. Same general concept, user runs a search, you collect the data, UBI, but now you're building a ranking classifier. That ranking classifier then is able to learn a generalized relevance model that can apply to future results to boost things up and down. It can be based upon something very linear, like just here's the weights for different fields, or it can be way more complicated using deep learning models and those kinds of things. Again, not going to spend much time on this, but chapter 10 in the book covers building and deploying learning to rank models. 11 covers automating learning to rank with click models. So this is learning implicit judgments from the user's behavior and using those to train your learning to rank model automatically. And then chapter 12 is on overcoming various ranking biases from these models through active learning. And then the last category is signals-based knowledge graph learning. So in this category, this is the shortest one, very simple, but when users run searches, they do things like type a misspelling and then follow that up with the correctly spelled version. They type something and then they refine their search. All of these actions, if you tile these behaviors together and tile these textual queries together, you can learn very useful things to power your search engine. For example, over here on the left is one of the listings from the book where we're finding related items. There's a bunch of calculations that happened before this. This is just the final one, combining them with, sort of a composite, PMI, point-wise mutual information score, and just a popularity. But I can do things like learn that iPad is related to HP Touchpad, iPad 2 is related to iPad, different categories, different brands, things like that. I can also automatically identify misspelling. So iPad period is a misspelling of iPad. HP Touchpad 32 is, hey, you just want to be searching for HP Touchpad. This is, probably just the number of gigabytes or something. Touchpath is touchpad. Tokepad is touchpad. Well, laptop, etc. These are obviously, misspellings are things that we do commonly, but if you're using an out-of-the-box misspelling capability built into an open source search engine that is based upon your index, you're not going to have the context of what your users are actually searching for, what they're actually doing, and what they actually mean. So in almost all cases, you're going to get way better, at least more pointed results, more refined results using signals, assuming you have enough signals. So there's 3 chapters on knowledge graph learning and using this type of technique to power semantic search. Chapter 5, knowledge graph learning, 6, using context to learn domain-specific language, and 7, interpreting query intent through semantic search, where we focus on lexical, sort of sparse vector-type semantic search. I like to combine all these techniques into pipelines, so I don't tend to think of one or the other of these techniques, but this is just like a Swiss, it's a toolbox, so it's, the book is like a Swiss Army knife that shows you how to do all these things and combine them in different ways. But there's lots of modalities you want to combine. And at the end of the day, your job, if you're focused on relevance for your end user, is to try to take sort of your understanding of the content. This can be the text you've got and lexical keyword search, those types of things. Take your understanding of the user. So that's, if I look at pure user understanding, that's something like the recommendations and collaborative filtering. And then take your understanding of the domain, which is a knowledge graph. It's a representation of the domain-specific language and the category in which your search engine operates. And if you sort of look at the intersection between the content and what you know about your domain, that's where you get into semantic search, whether you're using dense vector capabilities from LLMs to understand the meaning of words, or whether you're using something like the knowledge graph learning techniques I was just showing. And if you look at the intersection between understanding the content and the user, then you've got personalized search, which we talked about today. And then at the end of the day, if you can combine all three of these, that's where you really get at user intent. Because you're not just running keyword searches, you're not just recommending based upon behavior, you're not just noting what the word notebook means in specific contexts. What you're doing is you're combining all of the context available at the time the user's running the search to interpret and understand, hopefully, exactly what the user means by these words at this time in this context, and then give them the most relevant results, combining all those contexts. So as a summary, 4 different types of reflected intelligence models that we talked about today that you can build with user behavior insights and with code in the book. One is signals boosting, the other is learning to rank, the third is collaborative filtering, and the fourth is knowledge graph learning. I'm not going to go over the definitions again because we just went over that. If you're interested in learning more, interested in playing around with this data, if you maybe want to set up user behavior insights, start collecting some of this data, not just for pretty graphs and not just for analytics to tell your product team how things are going, but actually to build models to improve the relevance of your search engine to get better results for your end users. Here's the book. There's a 45% discount code. I don't know, it's about valid for like a week or so for anyone attending the conference if you'd like to get a copy of it. And then here's just some of the techniques that we cover throughout the book. And that is it for me. I've got 2 things to say real quick. 1, thank you for coming. 2, if you would like to get any help or assistance with anything you're working on in OpenSearch or otherwise, feel free to reach out. I have a consulting company, Search Kernel. Also, if you're a client of Open Source Connections, I'm a technical advisor for them, so you can get access to me through them. Grab a copy of the book. And also, the book is not released yet. It's coming out in a couple of weeks, like it's at the presses now. Literally 10 minutes before this talk, I just got a shipment of preprints of the book that I haven't even opened yet. So this is a weird thing to ask in a public talk, but if anybody has a box cutter, please come up to the stage. You got me? I would love to open these. This is going to be my celebration for getting the first physical copy of my book in my hand. But along with the book, we're also launching an AI-powered search community. We've got about 220, 230 people in there already, search experts from across various companies. If you like search and AI, or even if you just like search and you want to learn more about it, please, there's a QR code. You can scan it and join the community, talk and interact with us, and just keep up to date with all the latest going-ons in the world of AI-powered search. So that's my talk.